Hello everybody, I hope you are learning probability well. So welcome to this next video on this course, which is Introduction to Probability. So what we have done till now, so in the last few videos we have just reached that we have talked about sample spaces and we have talked about probability law, right? So these are the so let me just make a picture. So you have an uncertain situation. You are trying to make a model for this situation. So you have an uncertain situation, you want to have a mathematical model, and for that you have that mathematical model has two components. One is the sample space and the other one is the probability law. And we saw that if sample space has finite number of outcomes, if sample space has a finite number of outcomes, right, then in the last video, in the third video, we saw that how to define probability law. So for that we had this discrete probability law which we discussed in the last video. Okay, so in today's video what we are going to do is we consider if the sample space has if the sample space is continuous, right, then how do we define probability, right? Then how to define probability. So this is the topic for today's lecture, how to define probability law. So that is why I have given this topic as continuous probability law, right? So if you have not seen my previous videos, then please go through those videos so that you understand the next concept well. So okay, so let us just consider that let us just revise that what our probability law is. The probability law is your it is a function from set of all events to 0 1, right? So it satisfies some properties that probability has to be greater than equal to 0. Probability of A union B should be probability of A plus probability of B if A and B are disjoint, and then the third one is that probability of whole sample space omega should be 1. So omega is my sample space. So this probability this property we call as positivity, this is additivity, and this is normalization, right? So this is the three properties which we expect from our probability law, right? So let us just consider some examples and try to find out that how we can define the probability in case when the sample space is continuous. So first of all, it should be clear to you that when is your sample space discrete and when is your sample space continuous. So it's very simple. So you can consider example 1. This is tossing a coin, which we have discussed in the last video. So here there are only two possible outcomes, head and tail. So this is discrete, right? So you have only finite number of outcomes. And then you look at this example 2. So here what example I'm taking is you have a wheel of fortune, right, and it is continuously calibrated from 0 to 1. So we have a wheel of fortune and it is continuously calibrated from 0 to 1. From 0 to 1, it means that it can you have a wheel, right, and you just spin that wheel. You can get either number from any number from 0 to 1, right? Now if I ask you how many numbers are there between 0 to 1, so you have basically an interval. This is the possible outcomes, and this interval is having uncountably many elements, right? So you have uncountably infinite number of elements. So this interval has uncountable infinite number of elements. Okay, so now the question is, how do we assign a probability law in this case? So we have let me tell you what I am doing is I am having this example that you have wheel of fortune, and when you spin it you can get either number from 0 to 1, and there are uncountable infinite numbers in this interval 0 to 1. So I would like to ask you, what will be the probability? Say if I ask you what is the probability that I get a number equal to 0.5, getting 0.5. Can you think for a moment that what should be the probability, right? For example, let us just compare it with the last example. In example 1, which was tossing a coin, right? Probability of head was 1 by 2 and probability of tail was 1 by 2. And here, if I ask you what is the probability of getting a number which is 0.5. So this is example 2, spinning wheel whose possible outcomes are between the interval 0 to 1. Now suppose if you say that this is some number, say alpha, okay, then what will be the probability of this, of getting of whole of the image? This is your omega, right? Sample space, because these are the all possible outcomes. Then what is the probability of omega? That will be alpha plus alpha plus alpha plus alpha plus alpha plus, so because it contains uncountable infinite number of elements. So this is uncountable infinite number of times, because omega is your 0 to 1, and you are saying that for a single, for example 0.5 or 0.6 or 0.555, I'm saying that probability of getting a single number is alpha. Then what is the probability of whole of the sample space? That will be alpha plus alpha plus alpha, and you will keep on adding. So this number for surely will be greater than 1, which is greater than 1. So this contradicts our normalization property. So normalization property is not there. Okay, not satisfied. So obviously it means that we don't want this to be true, right? We cannot give any probability to a single, getting a single number in this continuous case. So for sure we have to put that probability of getting a single point in the fortune wheel is 0, right? So in this case, you see, do you remember that in example 1, what we have done, we have assigned probability to the outcomes, single outcomes, and then we have defined probability of any event E as sum of the probability of single outcomes, where E was containing AIs. So this is what we had done, that in case of a discrete sample space, we will assign probability to the single outcomes, and then we will compute the probability of an event by just adding the probability of single outcomes which are there in the event. So that where there we had used this additivity law, right? So but here in this case, because I told you that to comply with normalization property, so you have to assign zero probability to single event, right? So that is sure, right? So what we can do in this case, is, you see, your possible outcomes are from 0 to 1, right? So this is your sample space, this is my sample space omega, So what I am doing here is that I can just, if there is any interval, say a to b, right? So there is any interval a b, right? So probability that you get your number in the interval a b, right? So probability that outcome is in a b will be equal to length of the interval a b, right? So that will be equal to b minus a. Fine. So this is how, if I define like this, then obviously, because you are talking about length, so it means that what we are saying, that probability that outcome is in set A is equal to length of the set A, right? Now here you had an interval, so you can simply compute the length a b minus a. Now if I give you what is the probability that outcome is in this set to say a b or c d, right? So it means that your event is this whole, you want either it should be in AB or it should be in CD. So how you will compute the length of this set? This is your set A. So you will say that B minus A, this is length of this particular interval, plus C, D minus C, the length of this particular interval, right? So it means that we are saying that probability of outcome in set A is equal to length of the set A. Then obviously probability is greater than equal to 0 because length is greater than equal to 0. We know that length is defined as greater than equal to 0 thing. And also if you have A and B are two disjoint sets, then probability of A union B will be length of A union B. And obviously if A and B are disjoint, then this will be length of A plus length of B, right? So this is because A and B are disjoint, right? So that is it means that additivity law is also true. So this will be probability of A, this will be probability of B. And also what will be the probability of your whole sample space? Your whole sample space is 0 to 1, right? So your A is 0 to 1 sample space, right? So here let me write down omega. Omega is 0 to 1. So probability will be length, which is 1 minus 0, 1. So it means that if I define this as my probability law, then all the axioms are true, right? So I can, in this case, you can define this as your probability law, right? So now the question may be, sometimes it may be difficult to compute the length. You know, here I am giving you simple examples. If I give you that probability, your set A is set of all rationals in 0, 1, right? Then you have to think about how to compute your length, right? So do you know what is the length of set of all rationals in 0 to 1? So you can explore this question. Here you have to use your knowledge from real analysis, right? But because our subject is more concerned to probability only, then that is why we will stick to simple cases where it is easy for you to compute the length. But let me write down it as a note that sometimes computing the length of an interval length computing is easy, but if the set is not an interval, for example here the set is not an interval, right? Sometimes computing the length of a set A may be difficult, right? So you may have to use your knowledge from other subjects. So here you see I gave you that how can you define the probability when your sample space contains infinite number of elements. So basically we can say that the sample space is continuous, right? So I will give you one more example, so that is interesting. So let me write down the statement of the example and then we will talk about it. You can meanwhile think that how we will be solving this. So we have this Romeo and Juliet have a date at a given time, right? So it means that they fix a time for a date, right? And each will arrive at the meeting place with a delay between 0 to 1 hour, okay, with all pairs of delays equally likely, right? Okay, the first to arrive will wait for 15 minutes and will leave if the other has yet not arrived. What is the probability that they will meet? Right? Okay, so I hope you understand the problem. So there are two people, Romeo and Juliet. They have a date. Suppose this is the fixed time, right? So this is the point of time which is fixed, right? Okay, let me draw it here. So you are saying that they have a fixed time. So this is the fixed date time. Okay, so they must have fixed, say, 4 p.m. At some particular day. And each will arrive at the meeting place with a delay between 0 to 1 hour. So what we are saying is, Suppose this is 0 to 1. So let me call it as origin. So the fixed day point, which is the fixed date time, I am calling it as origin. So 0 to 1 hour, this is the delay by Romeo. Okay, and similarly, Juliet can also arrive late by 1 hour. So this here is delay by Juliet. Okay, so it means that they can this is your sample space, right? So it means that if I look at this point, it means that here, suppose this point is 3 by 4 comma 3 by 4, it means that Romeo and Juliet, they arrived at the meeting place after 45 minutes. They both have the same delay. They are reaching the destination after 45 minutes, right? So it means that this is the sample space. So sample space is unit square. So do you understand? So you should understand what sample space is denoting here. So sample space is here is set of all possible delays pairs, because here we have two delays, one by Juliet and one by Romeo. So this is the set where there are all possible delays. Now if I ask you how many elements are there in this set, so obviously because this set is a continuous set, so it has uncountable infinite number of elements. So this is a continuous set. So here we have to think about a continuous probability law. So it means that the probability of one single outcome is 0, because I have explained you in the last example that you cannot have a probability of one single outcome, because that will make that the probability of the whole of the sample space is greater than 1, which will contradict our normalization property. Okay, so how do we define the probability here? So in the last example we had a one-dimensional problem. So we defined the probability of getting an outcome in a particular interval as the length of the interval. Here what we can say, that what is the probability that this is the outcome is here in this region, say A. So what is the probability that outcome is in shaded region A? So I am defining it as area of A, right? So obviously because area is always positive, so we have this greater than equal to 0 thing. And also if A and B are disjoint, then probability of A union B, which is area of A union B, that will be, because they are disjoint, it means that one is here and one is here. So what will be the area of their union? That will be sum of the individual areas. So that will be area of A plus area of B. So that will be probability of A plus probability of B. So I have this positivity thing with me, and I also have this additivity thing with me. And also in this case, what is the area of the total sample space? So area here is total sample space is 0 1 into 0 1. So what is the area of this unit square? That is 1 into 1. So that is 1. So normalization is also there. Okay, so by this time it should come to your mind that if instead of 1 you have a 10 here, then maybe you will define outcome in the shaded region as area of A divided by 100. So whatever is the total area, so that you have this normalization property. But that is not a very big deal. You can always modify that thing, right? Okay, so this is how I am defining my probability. So you agree with me that this can be used as a probability law, because it is satisfying all the properties of the which are expected from a probability law. Now what was the question? Question is, what is the probability that they will meet? Okay, now here we read the statement again, that Romeo and Juliet have a date at a given time and each will arrive at the meeting place with a delay between 0 to 1 hour, with all pairs of delays equally likely, right? So there is no biasness. The first to arrive will wait for 15 minutes and will leave if the other one yet not arrived. So we either one of them will wait only for 15 minutes, right? Otherwise they will leave. So now we want to compute the probability that they will meet. So let me draw again. So we have this as our sample space. So this is my meeting time. So this is delay by Romeo, Romeo's delay, and this is delay by Juliet, Juliet's delay, right? So now see, suppose this is 15 minutes, so 1 by 4. So these are 15 minutes from the time of meeting, and here is also this 15 minutes, 1 by 4. So you see, I am drawing these two lines. This is 1 by 4, not 1 by 4. This is basically this length is 1 by 4, and this length here is 1 by 4, right? Okay, now you see here, this area, what is this area? This area denotes this particular yellow shaded area. Can you think of what this area is? This area is that, so look at this point here. Delay of Juliet is, if you just look at this particular area, this much, right, this much here. So here delay of Romeo is only 15 minutes from the time of meeting, and Juliet is more than 15 minutes. So obviously here they cannot meet. Okay, now look at this point, these points. Here the delay of Juliet is like, it's more than 1 by 4 for sure, and for Romeo also the delay is more than 1 by 4, but their distance is more than 15 minutes. So here also they will not meet. Similarly, in this area here, the distance between their meeting, like their arrival, is more than 15 minutes. Can you check here? For example, at this point, so delay by Romeo is say 45 minutes, and delay by Juliet is less than 15 minutes. So obviously they will not meet, because the delay by both of them, the distance between that particular thing should be less than 15 minutes. Then only they will meet. So it means that this is the only region, this is the possible region where they will meet. So if anybody is arriving within this region, then they will meet. So this is the region where they can meet. So now what is the probability that they will meet? Equal to the area of this region, area of gray region. So what is the area of gray region here? So can you compute? So this is, total area is 1 minus area of yellow triangle, plus area of blue triangle. Right, now what is the area of yellow triangle? So this length is 1 by 4. So this length is 3 by 4, and this length is also 3 by 4. So area of yellow triangle is, this is 1 minus area of yellow triangle is 1 by 2 base into height. Right, and then similarly area of blue triangle is also, this is 3 by 4 and this is 3 by 4. So this is 1 by 2 into length into height. So angle here is 90 degrees, right? It's not a problem. So this is 1 minus 9 by 4, 9 by 16. You can compute, right? So this is 7 by 16. So this is the probability that the two will meet. Okay, now you see here in this video I have tried to give you an idea that how you can define continuous probability law, right? I hope you understand. If you have any doubts, please write in the comment box, and please study and practice more problems, so that you have you can grasp this concept nicely, because this is somewhat different from what you generally study in mathematics, right, in general. Okay, so please share this video and subscribe to this channel. Okay, thank you. Keep supporting.